Welcome, everyone. So today, John Cobb is here from Auburn University. He's going to tell us about multigraded syzygies.
Thank you for the opportunity to speak. Before I start, I wanted to say that I'll be here at Fields until the end of the month, so I'm eager to speak to people. And I'll mention some potential projects during the talk, but I've been thinking on a lot of different stuff lately. And so I've come at a time where I can be sort of maximally annoying to everyone else. So if you're interested in any of these things, like come talk to me, or about anything else. But this maybe will save you the trouble of being like hunted down. Maybe. Okay, so today I've wanted to talk about two projects that I've worked on that are all related by this title. And stop me at any time for questions. So first I wanted to talk about the main object that we're studying is these syzygies. So a syzygy of a finitely graded module is just is given by its minimal free resolution. So it consists of its generators. These are like the first syzygies, and then you have relations between these generators. This is your second syzygies. And you maybe have relations between those. That's like your third syzygies, and so on and on and on. And all this together gives you all the information about your module. So this helps you understand it in sort of layers. So these make up the steps of your free resolution. And if you are looking at a quotient, then this sees the geometry of the variety that you're looking at. And so the moral is, but these are hard to find. And the moral of syzygies is that if you just figure out partial information, like how many there are, what degrees they are, this can tell you things about M and the geometry. And so these are presumably easier to find. So you may wonder, like if this process ends. So Hilbert wondered this in 1890, and he found out that it does. So there's so the number of syzygy modules is bounded by the dimension of the ring that your modules inside of. And this is called the projective dimension. And these partial information, like the ranks, if you know all the ranks, then you also know the Betti numbers. And so this gives you the Hilbert polynomial. This gives you the dimension, the genus, the degree of the variety you're looking at. And there's still open things that are being resolved here. So there was like this total rank conjecture that was settled by Walker and Keller, which I'm saying now because he's here currently. So this is things that you know from the ranks, but there's also information that you can just get from the degrees, and this is certainly being worked out currently. So the first highlight are these NP conditions. So this links the existence of lots of linear syzygies to sort of better and better geometry. So there's this whole program that's like connecting like your embedding being sufficiently ample. So like, for example, if you have a canonical curve, then you can see what's called the Clifford index, which is some geometric fact. And then you can link lots of linear syzygies to seeing certain secant planes that are inside of your variety. Another thing, which I'll be talking about much more, is this regularity, which I'll vaguely say is related to algebraic complexity. So by this, I mean there's work that puts the complexity of computing a Grosvenor basis in terms of this invariant. So in this talk, I'll be talking about these two things. Cool. So first, I want to try to summarize an active trend in research that in the past few years, and what all of our attention will be in for the talk, assuming you don't get bored and spaced out. I know lots of people here have papers following this trend in the audience. So the question is, as I go from the left to the right, so here's just like a normal polynomial. And if I add a z grading, so this has degree 2, then I get better tools. So for example, now I've gotten things like Nakayama's lemma that you didn't have before. And as you add finer and finer gradings, you should have access to better and better tools if only we understood everything that was going on. So we want to move sort of facts that we know here into facts to the right-hand side, which are still maybe computable due to being in bijection with these sort of combinatorial objects. Cool. So and these extensions help us understand the sort of old situations better. So like, what does linear mean in this case? There's different, this splits apart. So like if you have some notion of linear here, perhaps it splits apart here, and then you can see what notions, what did you mean by linear? What made a theorem work? Cool. Okay. So let me go back and define this regularity, which I said was like algebraic complexity. So right. So this is like an algebraic definition that was given by Eisenbud and Goto. But essentially, let's just do like an example. Essentially, it's saying that if your regularity like D, then nothing tricky is happening past degree D inside of your module. Everything behaves as you might expect. So here's an example. Here's a particular quotient. And you go through, you look at sort of the max twist in each spot. So this is 0, this is 3. You then like subtract off this sort of like linear thing, and then you take the max. So in this case, we get 2. So right, and yeah, and indeed, this is like you can write this. Okay, but now let's talk about the most important result in regularity to date. So this was said by Eisenbud at least in 2005. It's this result that if you have a curve that's non-degenerate, so this means that you couldn't like put it into a smaller projective space. So this is truly like the smallest projective space you can put it, so it's not in a hyperplane. And it's integral, so like one piece. Then the regularity, you already have a sort of God-given bound in terms of this like geometric data on the right-hand side. Right. So this is sort of kicked off some results that there's a bunch of work that came off from here, which I'll talk about. But basically, if we go, so for this example, like the twisted cubic, you can read off the regularity has to be less than 2. And one take-home fact is that this gives you a bound on the degrees of the generators of your variety. So this should be cut out by quadrics. And this is like a well-known fact. Cool. Cool. And so my question is there a multigraded analog to this particular result? Can I get a bound in that previous example? So like there is a multigraded analog of regularity that was given by McClagan and Smith in 2004. So in the Z-graded case, so I should have said that when you're sort of D regular, you're also D plus 1 regular, D plus 2 regular, and so on. But now if you're Z 2 graded, then you have this region. And you have a lot of the same sort of facts. So for example, you still get a bound on like the multi-degree of the things that cut you out. But the connections are more subtle. So like, for example, like the regularity in the singly graded case is in bijection with like certain resolutions that you can find. But in the multigraded case, you can find counterexamples to this. And you can have regions that have sort of like infinitely many sort of these like staircase regions. This can go on for like infinite. This is something that would not happen in the Z-graded case. Right. Any questions so far about this? So there is an analog like this. So Lozovanu is a student of Lazarsfeld, proved that if you had something in like a product of 2 projective spaces, then you have some bound that's given to you. And this theorem that I'm advertising does it for an arbitrary product and has like a slightly different, less stringent definition of what we mean by non-degenerate in this case. So as an example, like if you take this just this random curve that's parameterized in this way, then you can read off at least a bound that comes from this theorem. And this is like the actual regularity that you can compute with Macaulay 2 due to Maverick inference. Cool. But more importantly, this has some like, right. Sorry, 1 second. Yeah, there's some directions that I want to like advertise. So this the techniques here are using this like kernel bundle techniques that were being developed at this time, which tells you like this, there's this bundle that controls sort of how the syzygies behave on your variety. And here are two projects that use very similar techniques that I think now we have blueprints to do. So the same sort of argument was used to establish sort of the biggest advance towards proving something called the Mukai conjecture, which tracks the NP conditions of certain kinds of, these are like adjoint line bundles, the NP properties of these. So this has been studied for toric varieties, but the NP property is like we throw away the multigrading. So in the examples that's been done in the past, and I'm wondering if you can do the same thing, but have a sense of NP that relies on a definition of linear for the multigraded case. I think I just said that it like is related to having like lots of linear syzygies, and it's actually just like the number of steps that you have in your resolution until you like no longer just have linear syzygies, so it like jumps up to quadric or something. No, I mean there's like relations between these. Like perhaps if you know regularity, then you know something about this. But there's some relation, yeah. So yeah, NP would tell you. This regularity would, if you're writing down a Betty table, the regularity would be like the height. The NP condition would be like how long this strand is until you bump up. So there's some relation because it makes your table like smaller. Oh, okay. Yeah. No worries. Great. And then also like the same things that happen with a curve, also you can bootstrap up to sort of arbitrary smooth varieties. So the same sort of techniques work here. If you make some, you have to do some sort of like generic projection stuff, but basically the same techniques apply. Yes.
What's the explanation for linear syzygies at the beginning, uninterrupted first, being especially good over just like lots of linear syzygies?
Oh, you mean like just distributed throughout rather than having the first step or steps? I think this is a good question. I think like I think it has historical reasons. So for one, like there's like a bunch of results that was done by Petri and Noether that like said that, for example, your canonical curve is generated by quadrics. This is telling you that sorry, maybe I should write. So like, so your canonical curve is generated by quadrics. This is telling you that your canonical curve at least satisfies in 1. Or that's projectively normal. This is like in 0. So in short, there's a bunch of classical theorems that were reorganized into the NP conditions by Green in this paper. Yeah. And also like the first place where this stops, where you jump up and stop having linear syzygies, like in a lot of cases, we know exactly like the things that are here. And it has like geometric consequences. So it's like tied to, it's tied to like there are existing certain like secant planes inside your variety, which is really cool. Yeah, thanks. Any other questions? Yes, please.
All start in weird points, but now like you are just looking at like each of those individual points.
Yeah. Yeah, right. Like I think we need to examine what we mean by linear, but like there's a lot of papers like where like if your degree, if your degree was here, like 1, 1, then maybe the degrees in the next step are at most like this staircase region, or these, sorry, no regions, sorry. If your first degree is like 1, 1, then perhaps by linear, what we mean is, I need some colors, like that your next syzygy should be at most this multi-degree, and so on. So this is like the best you could possibly hope is for these to maybe advance by 1 in each direction. Yeah. Yeah, so yeah, this is all for like a toric variety that whose Picard group would be z to the n. So I think any smooth. Okay. Cool. Thanks for the questions. So yeah, it's like, and yeah, and I guess I'm suggesting that both of these have analogs for products of projective spaces, but also they probably have analogs way further because the main techniques that are being used here are these things called valence and resolutions of the diagonal, which are like God-given resolutions that are given to you in the product for projective spaces. So the real technique that's useful to you is that you can get a Balancen's type resolution on the product by sort of pulling back these known ones. But now there's like a very recent generalization of this like important tool, going by the Hanlon-Hicks-Lazarev resolution, which has only recently been churned from sort of like symplectic geometry into a more palatable like combinatorial picture, like cellular resolutions. And this is like something that's happening now with the people in the room, which I'm eager to understand. Tell me about it, please. Cool. Cool. And this is everything I wanted to say about regularity. And now I'm going to shift into something completely different. So if you have any like questions, let me see what my timing's like. So normally I have a, okay, cool. Yeah, please. Yeah, sorry, I feel like my pacing has been a little strange here, so please ask me any questions. I'm happy to. Yeah, thanks. Yeah, so yeah, again, I'm just suggesting that the same sort of techniques that I like have not really explained that was used to prove this are also used at length for these two important results. And I think there are analogs that go as far as toric varieties, or if you're brave, like toric stacks, I guess, because there's the HHL resolution for those as well. Maybe I'm not so interested in that. Okay, so going back, because I like it so much, the Hilbert-Syzygy theorem. So this gives you a bound on the projective dimension. And then like 110 years later, Stillman asked a question, like a follow-up question. So he thought maybe there's like a problem with, like, often we're in the business of getting a bound on your ideal that doesn't depend on the space you're in. Like you want intrinsic properties, right? So like he's curious that if invariance of I, like the projective dimension, he asked it for the projective dimension, can be bounded just in terms of like the generators of I, so like the number of degrees of them. And so the important bit about this question is that the bound is independent of how many variables are in the ambient ring that you've just kind of arbitrarily chosen. So you can always re-embed. Right. So let's do an example. So here's an ideal, and for some reason I want to know its projective dimension. So I haven't been given the ring that's inside of. And so what you could do, you could be like, oh, it only has x1 up to x18, and you could put it in this polynomial ring and get the bound 18 from the Hilbert-Syzygy theorem. But if you give each variable degree 1, then this is just generated by 3 cubics. And if Stillman's conjecture is true, we have some bound from this information alone. And this one has been computed. It's like 5. So give me any 3 cubics. The projective dimension is at most 5. So here's the story. So in 2000, Stillman conjecture is what's known as the Stillman conjecture. Though the funny thing I've come to understand is that Mike just wanted this for like an actual application. Like he was asking people like, please, can you tell me a bound? And then what happened is that he proceeded to get like 3 proofs that there are in fact a bound, but without computing it. Like it's very hard to compute this bound. And and so I'm continuing this tradition. This proud tradition. And so it's been proven like 3 different papers as far as I know. The crucial concept is that of a strength of a polynomial. So this was like previously considered in number theory. Inside of this paper, like Stillman conjecture appears as like theorem C in the middle of A to E. So there's all these like, so the main point is that they made this thing that's now called the Ananian-Hochster principle, which I'll talk about, which uses strength to characterize a bunch of different, to get bounds on like, or at least the existence of bounds on like a bunch of different invariants. So there's this interesting sort of notion that there's like a strong universal statement about the sorts of properties that strength can detect. So it's a bit imprecise. Yeah, I'll just leave it at that. But there's interesting facts about strength having this universal property for like heuristic closed conditions. And 3 years later, it was proven again by Ehrman, Sam Snowden, and then again by Drasma, Lazon, and Lakin. And this got a lot of attention because they packaged up this non-Hoxter principle and this concept of like certain types of limit rings, which I'll talk about. Cool. Right, and like I've been suggesting, projective dimension could be swapped out with like a host of other things, like maximal codimension of an associated prime, regularity, the Betti numbers at any particular place, number of linear subspaces inside of. So the fact that, yeah, right. Cool. So here is a stupid counterexample if you change the grading. So here's a particular polynomial ring with like acute grading instead. Yeah, so what does a counterexample look like to Stillman's conjecture? So I posit this as one outside of the standard graded case. So I've given the variables like a stupid degree so that these are exactly linear forms. I've cheated. Yeah, this is like a designer ideal that has known projective dimension. So it's n+2. So this is a counterexample because I can increase, so this will always be a thing of linear forms, but as I re-embed it into bigger spaces, the projective dimension is getting larger and larger and larger. So like maybe we want to avoid doing this. So like we want to avoid having this like infinite decreasing sequences because I'm like changing the degree at each step to fix this problem. And this goes by the name of being well-founded. So let me talk a little bit about sort of assumptions that I can make in my grading. So like, okay, if you have something that's like just well-founded, this is not strong enough to ensure a Stillman type bound. And what I'll advertise to you is that this notion of like bounded factorization is precisely the thing that you need for all of these Stillman bounded properties to still have a bound in terms of the degree sequence. So this bounded factorization is a little complicated. It's just saying that you can't express an element in terms of arbitrarily long sums of other elements. The important thing to know is that this implies well-founded. And if you're finitely generated, then you definitely have this. So it's somewhere between well-founded and finitely generated. Right. So for example, in torque geometry, if you look at the Hertz book, the support, which I've defined on the previous page, sorry, I didn't really emphasize the support, it's not that. This is just like putting together the degrees of your variables is given by the effective cone. So this is like the name in torque geometry. Okay.
Wait, sorry, John.
Yeah. Yeah, sorry. So in this case, you have some Cox ring, and your degrees of your variables are given by elements in Z2. This is connected. It has bounded factorization. So the theorems I will tell you applies to this, for example, but also to things that have like infinitely generated Cox rings, which isn't that like crazy of a thing to study because I think like M013, for example, like the Cox ring of M013, 13 marked points, also has an infinitely generated Cox ring. You can like, yeah. I learned this like 2 days ago. It's a cool fact. Yeah, and so you can run into this in like in very short examples, like certain blowups too. And so the meta theorem is that if you have bounded factorization, this is precisely what allows you to do an Ananian-Hoxter principle. So for example, the rings that have bounded factorization are characterized by the fact that they have a Stillman. They have this the Stillman bounded projective dimension. So it's a bit wordy, But basically, if you have any degree sequence, there's some number that just depends on that. And then also maybe the support of the thing you're talking about. It bounds the projected dimension of any particular ideal that you give me that's bound like, with this degree sequence, as long as the grading has bounded factorization. So it's characterizing. Okay.
Okay.
Yeah.
So the bounded factorization, like your conditions on the grading,
Yeah.
are these things that depend only on the group that you're grading by or also on the specific grading?
Yeah, this is a great question. It doesn't depend on the particular, it only depends on the support. So you could change the way that you're grading and this would still apply. Yeah, right. So this is a great question and it leads me to my next example. So I'll pay you later. Yeah, right. This is what Stillman wanted, right? This is in gamma D was what he keeps on asking for, and we know for 3 cubics. So if you have 3 cubics in a standard graded ring, so this is like n, the natural numbers, I mean, not not some random, then I do not know what M gamma G is, and yeah, but for some examples, there's like really long papers that computes it. So for 3 cubics, the answer is 5. But for this, there is no hope that through the methods that I use, you would ever obtain this. D is like a degree sequence inside of here that describes the generators of like your ideal. So yeah, so you have some ideal and it's generated by some finite list. And each of these can be assigned, you know, the degree of each of these can be given some function inside the grading, the support. Yeah, it's just some, yes, okay, sorry, some number that's inside your support. And then D is like the sequence of these.
So gamma is saying the grading, not necessarily standard.
Yes, right.
So now if you replace this DI, if you have, for example, a standard grading, pull the D's apart. First of all, if you have a standard grading, you know more.
No, I mean, well, I can say that like we have some theorems along the lines that if you have like if your support's inside of the other, then you have then the bound that you get in this case is smaller than that one. So so you have some theorems like this where you could compare to known results inside the standard graded case, but nothing is like specifically more computable because of what's been done here. Yeah. Okay. Yeah. Please.
There are some bounds that are explicitly known.
Yeah. For sure.
But
Yeah.
these are like incredibly ambiguous. They're just used.
Yeah.
The tower station. So basically, it's impossible to even think of a number better.
Yeah.
They are indeed.
Yeah, for sure. Yeah. Yeah, and perhaps like, okay, perhaps this is a bummer. Maybe it's like, well, nothing's computable. But it's at least interesting to know. So for example, like well, I'll talk more about it, but like to have a result like this where you have like like a tight result, like what guarantees you such a bound? Like you're probably not going to get it with these like very explicit methods which require kind of more assumptions. So wait, maybe I'm saying too much. Let me just like go to our next example. Oh yeah. So that's just that in the 0th degree, or like you have just K. Just yeah. Thanks. Any other questions? So I don't know if I guess I'll do it. I think this would be nice. Maybe it's a what's that? It's like it's a weird example. So here's some like sequence of polynomial rings that like some daemon has given you, and like basically how you're assign a grading is for x0, you'll give it this grading, like 0, 1. And then for x negative 1, x1, you'll give it that grading, and then so on. The support of all of these is just like the degrees of all of these together. So it's some like infinitely generated thing. But these are each connected. They have bounded factorization. This is more instructive than it is maybe interesting. Like I don't, okay, so they still have bounded factorization. So you can find a bound for any list of, for any ideal that's generated by this, by any sequence inside of this grading. And in fact, like due to this fact that I barely said that you have this like inclusion, it didn't really matter actually how I graded these. They could be kind of done randomly. So it didn't need to be so orderly, I guess. I think I cut off a question just to say something else that was possibly confusing. Okay, cool. And then let's return to this other example. So here's the thing we were looking at before. The bound is definitely bounded by 5. If you give it this particular grading, then the degree sequence is like 3, 0, 0, 0, 3, 0, 0, 0, 3. And then the Stillman bound is 3. So it's exactly the projective dimension in this case. So in other words, by like changing your grading into like a finer one, the Stillman bound will become better. I don't, yeah, right. So I've cherry picked this so that this reveals the fact that the thing that I started with was actually a regular sequence, in which case the projective dimension is just given to you by the list. Like it's 3 because it's a regular sequence, which is 3 long. And this in this particular grading shows you this fact. Yes.
If the Stillman bound isn't explicitly computable, then that's 3.
Oh, just because? Oh, from this fact alone, rather than sort of figuring out it's a regular sequence?
Yeah.
Yeah. You can argue this basically from like some linear algebra about how these need to add together to give you something. And
So it's like this really specific example.
Yes.
Figure out that it's not, there's actually some cost examples for you.
yeah, this might be expanded somewhat, but like it's I don't, maybe not in an interesting way. It was more, yeah, it's just I think what I'm suggesting here is that like I don't know, like if you compute this thing over different gradings, you get finer invariance, and maybe this is exactly the projected dimension. I don't know. Right. Yeah, right.
And just, sorry, just to be precise.
Yeah.
When you say the Stillman bound, you
Yeah.
mean you mean you have exhibited a function of only the degrees that bounds the projective dimension. So you're using the Stillman bound to refer to any function of only the degrees.
Yes.
That
Yeah.
bounds the projective dimension. Or anything of that degree sequence.
Yeah, right. So this is like some number that when you input this and E, in this particular case, it's 3. Yeah. Right. Okay. So I want to talk a little bit, I don't know, like, I just want to talk a little bit about the machinery, because we have like some theorems that sort of like extend this beyond projective dimension, or like some other interesting sort of theorems in algebraic geometry. And it's super weird. Like, I think it's weird. Like I didn't, okay, anyway. So like, like I said, this Anand-Hoxha principle is what's important. It tracks the strength. So the strength is this thing that it's like, if you're strength 1, I'll say this. If you're strength 1, this is like, sorry, 1 second. Right, so if you're strength 0, this exactly means that you're reducible, so that you can be written as like a product of just 2 things. But maybe you're kind of close to being reducible. Maybe you can be written as like a product of like, maybe you can be written as like You know, like a length 2 such thing. So it kind of measures away how far you are from being reducible. And then you can upgrade this to the strength of a family, which is like the minimal strength of any combination of these. So it's for sure smaller than the individual strengths, and it may be even smaller due to some cancellation. So things that are strength 1 are like infinite. So this is kind of like saying that your variables, you can't decompose. They're irreducible. And any strength can be obtained, at least in the standard grading. But the moral here, like, I don't know, how important this definition is just that if you have like a sufficiently large strength, it becomes a regular sequence. Right. Okay. Yeah, so maybe I'll skip this. Okay, maybe I won't. Sorry, one second. Right, maybe I should say this. So this is the Ananian-Hochschild principle. This is like how it works. So what is a counterexample? I suggested that if you have a sufficiently large strength, it becomes a regular sequence. And for sure, if you take this to its extreme, if it's infinite, you can show it's like really short that these form a regular sequence for sure. And what we want to prove is that there's some number that detects when you become a regular sequence. And how a proof like this might go is that, well, suppose not. Here's a possible counterexample. You have a bunch of things of degree D. The strengths are increasing. So you have like unbounded strength. None of them are a regular sequence. You take some sort of like nice limiting object. This has infinite strength. And now I can refer to the fact that I know in this extreme case. So like I take a bunch of, so it's like the construction of a counterexample. Like I take a bunch of things that have some property that you want, but the strength is getting larger. And then inside of this nice limiting object, you have like an infinite collective strengths where things are easier. And then you need to infer that, well, you must have not started with something that, none of them were a regular sequence. So you find some contradiction. So you're not computing like a bound. You're just showing that if there were a bound, you would have a problem with this. If there were not a bound, then you'd have a problem with this argument. Sorry, thanks. Okay. And then what I'll propose to you is that this nice sort of limiting object is the ultra product, which is like some nasty thing. Okay, so the elements, so this is something that kind of elements in the ultra product are like they satisfy certain algebraic relations if and only if these entries satisfy the same relations among the family with like probability 1. So like using an ultra product to wrap up this argument is not completely new. There's like a whole book on using ultra products in algebra and like a flurry of papers, especially like in the 1990s. Each with like an introduction that bemoans the fact that algebraists don't use it. So like, so it's me, algebraists, like so like I also begrudgingly use this, and and I guess what I'm trying to advertise to you is that I've figured out some of the algebraic consequences of doing like mild amounts of model theory, so that you may use this without wading in this like swamp. So basically, so this is less explicit than many other options, but it has like extremely remarkable logical properties that determine basically all behavior of it. So like one of which, so for example, like why didn't we take like the inverse direct limit ring? Is because maybe it's not even meaningful to take limits of arbitrary sequences of polynomials. So yeah, but maybe I won't actually. I don't know. So like the ultra product is filled from something called an ultra filter, and the intuition is that the ultra filter contains like like all finite sets, but not all infinite ones. Or the other way around, you can take, yeah, cofinite sets, or you can take all cofinite sets. So it's this thing that like contains essentially all subsets. Yeah, maybe I won't get into it actually, but sorry. It's like it's very kind of unwieldy, but there's this nice intuition with working with it. Especially so this is what was done in the Ehrman Sam Snowden paper, but this was done entirely by hand, you might say. And so while we're seeing to what degree this would generalize, we couldn't shake that sort of all the arguments felt sort of similar. It didn't seem to be about algebra. So right, we begrudgingly did some like model theory. Well, what I've been told is like fairly introductory model theory, what I was grappling with. But all the arguments of an ultra product are essentially the consequence of three basic things. So first is believe it or not, Wush's theorem. Wush. Yeah. Why? I mean, yeah, I pronounced it wrong for a very long time. But basically, it says that all first order properties of the ultra product are exactly determined by first order properties of AI, of like the things in the family. And so then a proof of Stillman's conjecture becomes proving that being a regular sequence is first order, and therefore transfers between the limits and the objects that you yeah.
And first order is something that a logician says.
Yes, right. 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 So like this roughly means that you quantify over elements and not subsets when you write the corresponding statement in logic. Yeah. Right. So this is like not the way that it was done in like Ehrman Sam Snowden, for example, because they don't have a proof that this is in fact. Okay, so to summarize again, oh wait, I should say two more things. There's this other remarkable property that says that ultra products behave well when you add new symbols to your language, or just something that's normally like catastrophic in logic. So like because of like elimination of quantifiers or something. So like when you expand the language, you have no serious consequences. So you can, and then saturation says that ultra products contain all limits. Roughly. So why use model theory? Is because you can get a cleaner proof. So you can see exactly what is necessary for the Stillman balance, and you can prove things that you otherwise would not when you're working by hand. And so why haven't model theorists like already done this? It's because of like things that we're hiding here. So like this also roughly says that like, yeah, so I've noticed like sorry, one second. There's this trade-off in model theory between like objects, between things having nice properties and the ability to say nice things about in this object being something you even want to talk about in the first place. So like this says that like basically anything that can go wrong does go wrong. So here's what I mean. So for example, it would be nice if ultra products of polynomial rings were polynomial rings. Unfortunately, this is not true. Ultra products not even close to being a polynomial ring. It like contains the Taylor series, for example, but it's strictly worse. Because of this thing that it contains all limits. So if you take the element like 1 and then x squared and so on, and then take the limit, you get something of infinite degree, but that's not something that lives inside of a polynomial ring. So we define this thing called a degree bounded ultra product, which is like some substructure of the ultra product. And it's exactly the one that has these three things I've told you about. So we can still reason about it. So it's kind of like intermediate. It's something that you can say strong statements about, but you still have like nice kind of algebraic properties. And it's kind of forced upon you, we show, if you want your ultra product to even still be graded. And you get a bunch of things for free once you make this definition. So for example, you get this thing that we want about polynomial rings, about ultra products of polynomial rings becoming a polynomial ring. And this is like, these are the kinds of theorems that I would hope could be just packaged up and used in future applications. So like, so there's many other things this could be used on. So like, for example, there's this toric Hartshorne's conjecture. So like Hartshorne's conjecture is like, so if you have like a hypersurface, this is for sure a complete intersection. It's just because you only have one thing that generates it. Hartshorne conjecture that in fact, if your codimension is small enough, you're definitely also still a complete intersection. So this is true in characteristic 0, an arbitrary characteristic, and it's also been proven using ultra products. And so I haven't put up the statement because I'm like a coward that hasn't like fully crossed the T's, dotted the I's. Yes, please. Anyone? Yeah, sorry.
Used about that. So if I have like your xy, comma, yz, comma, xz, and my polynomial ring, I'm just gonna throw in, that's K2, and I know K2 wherever I put it. I'm just gonna put it in the polynomial ring with million variables. Then 2 is definitely less than a third times a million, but it's not a complete intersection. What am I missing?
Wait,
Sorry,
that's singular, right?
Okay.
Yeah. Yeah, for sure.
So I know how to use ultra products to build characteristics. So
Yeah.
is there like some characteristic ultra product construction they're using?
Would to do this in an arbitrary characteristic or? Yeah, I think like, for example, like if you take the ultra product of like, yeah, I mean, there's facts about like if you take the ultra product of a degree bounded ultra product, at least of like polynomial rings, then the new polynomial ring that you're over, the field is an ultra product of the fields that were in the family. I think this is like what allows you to say things about arbitrary characters.
So they have, I can see.
Yeah, sorry. Yeah. Cool. Right. Yeah, and so I'm saying there's something like this also for like subvarieties of toric things. There's some there's some bound that would tell you that you're a complete intersection as well. Okay, cool. That's I think this is everything I wanted to say.
Cool. What questions are there for John?
Yes, please.
So the second last slide, with the grade you had bold lambda, so would that mean bold lambda is a cell?
Yeah, right. Yeah, well, bold lambda can be horrible. So for example, the polynomial ring that you end up with might be in like a continuum many variables, and then
Number of variables, but if each little lambda is n, is bold lambda n, or is it again some ultra?
it's again some ultra product, you think?
Better way to ask my question, which is when they're doing stuff on arbitrary characteristic, are they building mixed characteristic things as ultra products of mixed characteristic things with the same characteristic? Are they building mixed characteristic things from like a bunch of different characteristic keys?
I do not know. I don't know. Yeah. I don't think it's like specifically. Yeah, I would have to look. I think it's just a consequence of the argument just being like not reliant on, like it's not handled separately. I don't think. I think it's just an argument that the methods that you're using aren't sensitive to the characteristic. Yeah.
So, question.
I never really thought of defining this and lambda. I just thought the question is it bound? Like, what is the boundary?
Yeah,
So. But then, it's correct that if you have a broker-based system, a number of generators is different. The size of the broker system.
yeah,
I don't know what.
yeah.
That kind of bothers me. Rates are relevant.
Okay, yeah, there's some subtle point about the projective dimension. Yeah, this is kind of subtle. It kept, so like the projective dimension is not sensitive to the grading that you've chosen. Yeah, okay,
The D is the degrees, right?
yeah,
It's the number of generators that matters as long as they well behaved enough. Like, for example, so if you take a monomial ideal, it's just a number of generators is the upper bound that it is realized, no matter what the degree, objective dimension.
wait, I think there's examples of, for example, like if you have three, if you have an ideal that's generated by three things, then I think you may be able to realize like almost any bad behavior that you would wish. So like it doesn't seem like this could be true. Like I think you'd be, yeah, without further restricting the degrees, if you just have the number, then I think the projective dimension could be like very horrible, very bad.
Yeah, but that's the question of again.
So this is like there's some theorem called Bruns's theorem.
I guess my question is it equivalent to how hard it is? Is it equivalent to the question of how hard is it to the same size of the building?
I think that's what might be asking this question.
Yeah,
That's the thing.
yeah,
Yeah, then it all makes sense.
yeah.
So I didn't know why that's.
Yeah. I think it was in context with that there was a known way to go from such a bound to one on regularity. And he wanted to know when a certain Hilbert like function became polynomial, I think. Yeah, but yeah, as a note, this Bruns's theorem says that like any tail end of any resolution could be realized by a resolution of S mod I, where I is generated by three things. So like almost any bad behavior that you would wish without restricting the degree can be accomplished basically by such an example, which I think is just like an abstractly interesting thing to think about. Yes, that's what I'm saying. Yeah, this is crazy. There's even a theorem in Macaulay too that you give it an ideal that's generated however many you want, and there's an explicit construction to give you this. Yeah, it's wild.
Any other questions?
Yeah.
Like
The
oh,
S,
S,
not C.
oh, sorry.
Yeah.
Yeah, sorry.
All right, let's thank John again.